Today, we're going to talk mostly about MATLAB isms in support of your own implementation of perceptron learning algorithm. So, a little quiz of sorts for you. In vector matrix format, what is the equivalent expression for the hypothesis, the current working hypothesis? H of x is sign, S-I-G-N, so it returns positive or negative depending on whether or not the parameter to it is positive or negative. The sum, I, goes from 1 to d, where d is the dimensionality, number of features for our representation. I goes from 1 to d of wi, xi, so it's the weighted sum. And then we add to that our plus w naught, x naught. I'll give you a moment. Please press pause, and I'll give you a moment to think about it. Okay, and we're back. And so the answer is h of x is equal to sign of w transpose x. Now, in this case, our w transpose is the following. So we have, let me change the color of the pen here. Let's change to that. How about we'll work with blue. And our w vector, in this case, consists of d plus 1 positions, w naught, which is that dummy variable that we added where w naught, it was a substitute for minus t, where t is a threshold. We have w1, which is a weight, up to and including wd. Now, of course, w1 through wd, those are the w's here in the original weighted sum. And w naught, this is our w naught. And so we represent that w vector as an augmented w vector, where the augmentation consists of the inclusion of an additional position, that w naught. And likewise, x is also a vector. Let me not forget our vector notation. And x originally consisted of x1, x2, x3, up to and including xd. That's these x's in the weighted sum. And our augmented x vector is going to include that x naught. Here's our x naught, and x naught was fixed to a value of 1. So x naught is equal to 1. And we have x1 up to and including xd. Okay? And so if we take our w transpose, well, if that's w transpose is just the row vector version of that same d plus 1 vector, including w naught, w1, up to and including wd, where each of these are the weights, as mentioned before. And if we multiply that w transpose, that's w transpose. So let me put that t. If we multiply that by x, our x has not changed. So we have x naught, x1, up to and including x subscript d. All right. So if we do this multiplication, w transpose x is nothing more by the rules of vector multiplication. That would be across this row, down that column, we multiply all of the terms, so w naught times x naught, plus w1 times x1, plus w2 times x2, up to and including wd times xd. Okay, so there's the answer. This expression, if we write it in vector matrix form, it's sign of w transpose x, where this w transpose x is the same as performing this operation, the parameter to sign. Okay, so project 3 is going to be posted on the Blackboard. It is due Tuesday, the 31st of March, at the usual 1 second before midnight, 11:59 and 59 seconds. And in this assignment, you will be implementing PLA on a synthetic data set in 2 dimensions representing the credit purchasing problem. Okay, and so to jog your memory, we have a number of records from historical data from a bank, and each record has D features. So there's the first feature, there's the D feature, and each one of these are attributes that you would obtain from the credit application. So things like the age of the applicant, perhaps the annual salary, the number of years in residence, right? Each one of these would represent each of these features corresponding to that vector valued input describing collectively a particular applicant. So we have a number of records. Each record corresponds to one of these vectors x, and we also have a weight vector for our linear model. That weight vector is also in d dimensions. Now, of course, we augment this as we had discussed before, and the goal is to try to find some hypothesis, some linear model that agrees with the ground truth labeling, which was the ground truth decision for approval being a +1, so-called positive example, and denial for credit being a -1. And so here we had this treatment where we took our threshold, and the idea here for classification was that weighted sum has to be greater than the threshold, right? So we had some sum. The sum I goes from 1 to d of wi xi, right? And of course, we're going to take this and we want to compare this so-called score to see if it's greater than some threshold t. Now, of course, you do a little bit of manipulation on this, and you subtract t from both sides of the inequality, and we have this expression, sum I goes from 1 to d, that hasn't changed, of wi xi minus t, right, because we subtract t from both sides of the inequality, is greater than now 0, because t minus t is 0. All right, so we have this expression, and we want to clean this up a little bit to make it more convenient, if as it were, to mechanize this computation. And so we have that expression here. Here's our weighted sum, right? And then here we have our minus t. And so we substitute or replace this constant minus t with w naught, and we're going to give this a different name. We're going to call this the bias, and that will be apparent quite shortly about what that means. And so we replace this minus t with a constant w naught, and so here we just take this minus t, and w naught is just a scalar. It can be positive, it can be negative, and so we can certainly replace minus t with it. And we're left with this expression. And then we include an x naught here, and this x naught is a constant value of 1, and that's the same as saying w naught 1 times w naught is equal to w naught. And so we're including our x naught, where our x naught has a constant value or has a value of 1, right? So that doesn't change this expression, and so we now write this w naught times x naught and make the observation that we can actually fold this term, w naught x naught, into our summation, and as a result, change the index so that instead of I going from 1 to d, I goes from 0 to d, and we write this sum I goes from 0 to d of wi xi. Okay, so we do that, and of course, as we saw at the outset with the little pop-up quiz, that's the same as sign of w transpose x, where the w transpose, where the w, this augmented w, includes our w naught, as well as the w1 up to and including wd, and this is our w transpose. And our x vector includes our x1 through xd, but it's augmented with this x naught, x1 up to and including xd. Okay, so these are they, and we can rewrite this hypothesis as sine w transpose x. And so this h of x is going to output one of two values, right? Depending on what that w transpose x is, it's either going to give you a +1 if this w transpose x is positive, or it's going to give you a -1 if this w transpose x is positive. And so the idea then is to find the w such that the corresponding hypothesis or linear model will return a +1 and -1 that's consistent or matches the ground truth +1, -1 labeling from the historical data. And again, +1 means that that person was approved for a loan, -1 means that that person was denied a loan. Okay, and so this makes the assumption that the data is so-called linearly separable, right? What that means is that you can take this straight line or a linear model, and you can use that or find a linear model that will separate the data into two groups. And so here we have one particular line on the plane. A linear model in 2 dimensions is a line on the plane, and this line separates the data into two groups, the group up here and the group down bottom. And the idea is to find some line that separates the points such that the groups resulting from that separation coincides with the ground truth plus 1 minus 1 labeling. And so that would be the following line here, right? And see if I can draw this on my sketch tablet. And this following line, you can imagine if this were a straight line, that would be the linear model that coincides with the ground truth class label. Okay, so this is our version of h of x, and that's where we left off last time. And then in our PLA algorithm, we're going to find a different w, a different linear model or line in multiple dimensions, and we're going to do that with the following update rule. So you can think of this w as being the old version, and you want to find this w, which is the new version. And so how you arrive upon the new version is you take some input x in vector form such that the hypothesis h of x does not agree with the ground truth target function. Not agree, right? So that means the class label, that label here, yi, that can either be a +1, that corresponds to these plus blue points, or it can be a -1, and that corresponds to these negative points here. And so if, for example, you had some xi, some point, let's say this one, right? And that one, its ground truth label, it's going to be +1. Okay, so that means the h of x, let's say if you called h our current working hypothesis on x, and that output, say a -1, and because +1 is not equal to -1, that means h of x does not agree with the ground truth label. So h of x is saying you should not approve this person for credit, whereas ground truth, this person was approved for credit. That means it incorrectly classifies that point. So we select some point among all those historical records, or we select from among them some point for which h of x, or some data point or some individual for which h of x predicts incorrectly, right? And when you get that incorrect point, so this is our incorrect point, right, for which h of x was not correct, you then perform the following update in order to find a new weight. And so here, the new weight is equal to the old weight plus the ground truth labeling +1 or -1, yi, corresponding to that particular point, xi. And effectively what that does is illustrated here in the diagram. So here we have our hypothesis, our current hypothesis. And this current hypothesis, when we do this update, we're going to select then a different w. So this is w old, right? And let's say when we did that selection, we got a different linear model, and let's say that different linear model was this straight line, right? You just have to humor me. It's not really straight, right? And we're going to call this line, we're going to call that w new, right? That's the new version of w that we get by performing this update. So this label here, it's +1. That's going to be yi. Yi is equal to +1 because it's a positive point. This person was ground truth approved for mortgage. And then xi is going to be the position, xi. That's going to have a certain number, a salary, and a certain number of years in residence. Okay? And so this is a point that was incorrectly classified because here we have that original hypothesis characterized by w old. It said, hey, you should be minus because you're on this side of the purple line. And then when it performs this update, the so-called PLA, perceptual learning algorithm update, or perceptual learning rule, it selects a new line, the blue line, w new, that corrects that point. And so that blue line, you'll notice this xi is now on the correct side of the line. It's a positive example now, so it corrects for that. Okay, so any questions? If you have questions, please post them on Blackboard, post them in the Slack channel, and I will certainly address it. Okay, so let's take a look at some MATLAB tips, and these are going to be some considerations for how you do this for real, right? How you plot them, how you interpret the data set. Now, when you look at a data set in reality, it comes in the form of a table. And that table here, let's take, for example, the credit classification, or the credit classification example. We're going to start out with 3 columns in the data, and this is going to be a CSV file, okay? And so that CSV file is going to have 3 columns. It's going to have the first feature, so let's call that salary, right? And the next column is going to have the second feature, and let's call that years in residence, right? So the last column, that's going to be the class label. We're going to call that YI, right? And that's either going to be, we'll just note that as drawn from a set. It's either going to be a +1 or it's going to be a -1. Okay. So for example, let's say the salary here was 30,000, right? And the years in residence were 5, and that person was not approved for credit, and there'd be a -1. Let's say the next entry, maybe had $65,000 a year as annual salary, and maybe this person was in residence 7 years, and let's say that person was approved for a mortgage +1. Okay, so now that's each column, each row, right? Each row is going to be represented as the particular input. So this is the first person in the historical records. This is the second person, PRS, and likewise, you're going to have up to some number n, where this is the nth person, right? And these are the applicants. And so here, this first column, you can think of that, well, you have each record as being the ith person. So this would be XI, the ith person, the first feature, XI1. And this would be the ith person, right? I can be 1, 2, 3, up to including big N. The second feature. And this is just going to be YI, which is the label associated with that vector X. And so here, we would, along the rows, we would identify the ith person here would be just the ith row in this table, right? So this would be the ith, this would be XI1, XI2, and this would be YI, the label for the ith person, and this would be the vector XI, right? So that's the setup in MATLAB. And so we read in the CSV file, and when we're going to do the learning, remember, when we're going to do the update, we take our X vector and we augment it, our ith vector, to have an X0, which is fixed to be 1, and then we include XI1 and XI2. So the first thing we want to do in any data set is we're going to take that data set, right, and then we're going to transform it by first peeling off that third column, which was the set of class labels. And so we're going to take our YIs, right, these are the YI values, and we're going to split them apart from one another. And this is going to be XI1, the first feature, XI2, the second feature, right? So we're going to split apart the class labels from the actual data. And then what we're going to do, we're going to take this data, right, these features, raw features, and we're going to paste them together with our X0. So this is our X0, and X0 is all ones, right? All ones in that column. And we're going to paste it together with these other 2 columns that we got from the original data, which is XI1 and XI2, right? So that's what we're going to do in MATLAB. And certainly we can use this information for the class label. This is either going to be +1 or -1 and so forth. We can use that to decide to either draw these coordinates, x1, x2, as a circle, a blue circle, or a red plus sign to represent red meaning the negative example and blue meaning the positive example. Okay? All right. So let's take a look at that. And I'm going to exit the show. Let me keep those annotations. And I have MATLAB up here running already. So let's bring that up and let's take a look at it. So I chose variable names to coincide nicely with the theory so that when you go back and you're trying to relate what's happening in MATLAB with what we talked about in class on the slides and in the video, it'll make sense. So here, these are the first individual, first feature, x11 and x12. So this is the first and second feature, the annual salary and the years in residence for the first individual that's a mortgage applicant. Likewise, we have x21 and x22, which is the first feature, annual salary for the second person, and then the second person, the second feature, X22, which is 7 years in residence. So then we have our W1 and W2, and I just chose them arbitrarily just to show you what's going on, and we compose our initial weight vector that's not augmented that consists of W1 and W2. So this is going to be a column vector. In MATLAB, you use semicolon to say this is the end of the row. So we have in the first row W1 and the second row a W2. Okay. So let's take a look at this. Let me run this. And as you can see, W, you can see that it's a column vector and it has 4 and 1.57. Okay, so now let's construct our x1 vector and our x2 vector using this first feature and second feature for the first individual and this first feature and second feature for the second individual. So let me step over that, and now we have our x vectors. There's x1, and we see that it is also a vector, has rank 2 dimensions, and this would be x11, the value of 1, and x12 has a value of 2. Likewise, for the second individual, we have x21 is 5 and x22 is 7. Okay, so now what I'm going to do here is I'm going to plot these feature vectors in feature space, and then I'm going to set the range of the axes so that it looks nice. MATLAB likes to try to resize the scale of the graph, and sometimes we don't want that to happen. Okay, so let's step here and compute a figure, and let's plot the first point, let's plot the second point, and let's fix the axes. Okay, so now that threshold, remember we said in the math that we had a threshold called W naught, called T rather, and W naught was set to be, that minus T was set to W naught. So here we're going to define a threshold, and we're also going to set W naught to be minus threshold, because if minus T is W naught, then W naught is minus T, right? So we're going to set a W naught to represent that threshold, and then we're also going to set an X naught that's going to be fixed to 1. So now, in this next step, I'm augmenting these vectors, x1 vector and the x2 vector, and I call it x1p and x2p in terms of variable names. And you'll notice here I have what used to be the first row of this row vector x1. So x1 was that row vector, x2 was that row vector. I'm now going to augment them so that there's going to be an x naught term, which is going to be the first row of this row vector. So we started out, let me go ahead and do that, and then I'll show you the result. And so we started out, here's x1, right? And here's x2. And we're going to insert a 0, rather an x naught, which is going to be fixed to 1. So now we have 1, 1, 2, whereas before we had 1, 2 for our x1 vector. And likewise for x2, we had 5, 7. We're going to include an x naught just before the 5, and now it's going to x2p is 1, 5, 7. So this is a 3 vector. You notice it's 3 by 1, so 3 rows in 1 column, whereas here it's 2 rows and 2 rows in 1 column. Okay, so now we augment that W vector, and that W vector, we're going to call it WP. So we start out with W1, W2 like we had before for this W vector, right? It's also a column vector, and the standard I'm using is that all vectors are column vectors in the beginning. So we have W, and we're going to insert a W naught. This W naught was minus the threshold, so threshold was 8. W naught should be minus 8. And when we augment it, let me step here and show you the result. We have WP is equal to minus 8 for 1.57, whereas W was is 4 and 1.57. And so here W is 2 by 1, 2 rows, 1 column, and WP is 3 by 1, 3 rows, 1 column. And that first position, we've now included that W naught. So you start out with your data in 2 dimensions, and you start out with your weight vector in 2 dimensions, a 2D weight vector, and then you augment each of them. Right now, when you augment your input vectors X, you're going to get a data set with some number of them. You're going to augment all of them, right? Not just one of them. And so now we're going to compute h of x. Now this is h of x for the second augmented data point and h of x for the first augmented data point. Now here, this WP. Now when I compute WP prime, let me show you down below. So if this is WP, right? It's 8 for minus 8 for 1.57. If I compute WP transpose is single quote, you'll notice it's now a row vector, 8 for 1.57. So I'm going to compute the sign, as we said before. If I say sign and I give it a parameter that's positive, 0.0001, it's going to return a plus 1. If I give it a parameter that's negative 0.0001, it's going to return a negative 1. So plus 1, minus 1. So here's sign W transpose X. So I'm going to take this W vector that's been augmented, WP, transpose it, and then I'm going to multiply it with X2, the augmented X2 vector, X2P, and the augmented X1 vector, X1P. Okay, so let's do that for the X2P and the augmented X1 vector, and we look at H1 of X, and that is a minus 1. So that means this classifier is predicting that the X1 vector representing the first applicant from the historical data, that predicts that it should be denied or turned down for credit, and h of x, the hypothesis for the second one, is saying that person should be approved for credit. So now we're going to take these weights, the original W1 and W2, not the W naught, and we're going to call them weights. So we're going to stuff them in a vector. So we take the second position, and the reason why we take the second position of WP is because WP is augmented so that the first position is occupied by W naught. So we take the second position and the third position, which is our W1 and W2 that we started with for the 2D linear model, and we take the W naught, which is our bias, kind of the preference for what that threshold is, if you will, and then we call this plot PC. Now, plot PC is a MATLAB API call. I encourage you to look at the documentation. It's quite good. But what it does, it'll plot the linear model associated with the weights and the bias. And so because it's a 2D linear model, it'll plot it in 2 dimensions. And so we set our weights, get them back, and then we plot PC. And you can see here, the red data point is ground truth, our approved person for the mortgage. The blue point is our ground truth denied person for the I keep saying mortgage, for the credit. And then this line is this W vector consisting of W naught is minus 8, W1 is 4, and W2 is 1.57, right? And so these are some tools to and considerations to get you started about how you think of the data, and then also plot PC, how you'd visualize the linear model. Okay, so let's stop that routine and let's go to something that's a little bit more sophisticated, and I'll explain a little bit about what this does. And so here we have a CSV file, and the CSV file is organized just as I had discussed before, where you have this table consisting of the first feature, the second feature, and the class label. And so let's run this, and this data set has 100 of positive examples, people who were approved for mortgage, for credit, and 100 negative examples, people who were denied for credit. And so num PT cat in this example is the number of points for each category. And so 50-50, 50% of all of the customer records in this case are people who are positive examples, and 50% are people who are negative examples. And so we set that number of examples, so a total of 200 people, because there's 100 who are positive examples and 100 who are negative examples. So this quantity, this sets the random number generator to something called the Mersenne twister, and it also gives you the initial seed for that number generator of 0. And the reason why that's important is for reproducibility, right? If it's a randomized experiment, you want to use the same random number sequence so you can reproduce your results. So step through that, and I'll leave it to you to look that up in the help doc. Now, low and high, that's going to be a threshold that's going to be used later for another time to set some random a range, if you will, for random numbers that are going to be selected for some other purpose, and I won't talk too much about that. So let's go down and let's read that data file. And if we look at that data file, well, you'll notice here it's 200 by 3. So it's 100 positive examples followed by 100 negative examples. And the columns, it's 3 because you have the X1 feature, annual salary, X2 feature, years in residence, and then you also have the class label. And so for this data here we're going to select out all of the data associated with the first feature and the second feature just for the positive examples. That's data 1, and the negative examples, that's data 2. Right. So here you'll notice we build a new array. That's our square, our new matrix. That's our square brackets, and the first column is going to be all the data. The first column going from the first row to number of points in the category, right? So that's give me the first 100 values in the first column. So give me the first 100 annual salaries. And then the second one says, okay, give me the first 100 years in residence, right? So that's the second column of the original data file, rows 1 through 100. Num of points in the category. So then for the negative examples, you're going to start at one more than that number of points in the category. So the first 100 are positive examples. That means the next 100 are negative examples. So here you're going to start at num point in the category plus 1 up through twice num p cat point cat, right? So that you do that for the first feature, the next 100, and you do that for the second feature, the next 100. And so data 1 is going to be all the data corresponding to the positive examples, and data 2 is going to be all the data corresponding to the negative examples. Okay, so we set all the points here. You can put them in an array, and then the targets, which is another name for the class labels, I can collect all the class labels for every single data point. Okay, so I compute the transpose because I want things to line up later on. But the important part to pay attention here is when I'm plotting, right? So I say, all right, well, plot the positive examples, the XY coordinate or the horizontal vertical coordinate, which is annual salary and years in residence. And I'm going to plot all of that data for data 1 for the positive examples. I'm going to plot it as a blue circle. And then I'm going to keep that plot because every time I plot on the graph, I don't want to wipe away all the stuff that was plotted before, so I hold on. And then I'm going to plot all the negative examples as red plus signs. I don't have minus signs that I can write. I'm going to turn on a grid so you can see regular increments of what the values are, and then I'm going to label the graph with the title. So let me continue here, and you'll see the result of this is figure 1. And I think I reversed the axes, but nonetheless, it's still self-explanatory. So on the first feature, I call that years in residence, and you'll notice here that's 0, 5, 10, 15, 20. And then the second feature, X2, is annual salary, so that's 5, 10, 15 times 10 to the 4, so it's 15,000. Let's see, is that right? 15,000, yeah. 15,000. Okay. And so here we see an example of a 2D plot, and this is the feature space representation of a very simple historical record that consists of customers to a bank characterized by their years in residence, the first feature, and the annual salary the second feature. Okay. So the goal then is to now build your PLA model and implement PLA to try to find the hypothesis using the PLA update that will find the line that minimizes the number of errors. And we will examine that problem in another sitting. Okay? All right. So I think with that, we're done. And with that, we will end here. And we will segue to call it short. Please make sure you are going in and understanding the PLA model and understanding this MATLAB, because we will make ready use of it on the homework assignment. So we will end there. We'll end early.